This is Mr. Picard with another geometry lesson. Today we're talking about perimeters and areas of similar figures. First, the lesson in 9 seconds. The ratio of the areas of two similar figures is equal to the square of the similarity ratio. For example, if the similarity ratio is 2/3, the ratio of the areas is 4/9. That's the lesson in 9 seconds, but if you didn't quite get it all, let's keep moving. Perimeters and areas of similar rectangles. Let's start with that. We'll work through this exercise to see if we can make sense out of this whole thing. Imagine a 3-unit by 4-unit rectangle. Imagine also that there are 3 different rectangles, each similar to the original. And what we'll do is we'll consider rectangles which are 6 by 8, 9 by 12, and 12 by 16. We're going to fill out the following chart. We have the rectangles listed on the left. We're going to determine their perimeter, and then their areas, and then we'll compare those values. Find the perimeter of each one. You may remember that the perimeter is equal to twice the width plus twice the length. And then when we find the area, remember that area of a rectangle is equal to base times height. So when we look at the original rectangle and ask what its perimeter is, we need to take 2 times 3, which is 6, plus 2 times 4, which is 8, and 6 plus 8 is 14. 14 units. When we calculate the perimeter of the 6 by 8 rectangle, we need to take 2 times 6 plus 2 times 8, so that's 12 plus 16, and 12 plus 16 is 28. Over here we have 18 plus 24, which is 42, and finally 24 plus 32, which is 56. So those are the perimeters. Now let's talk about the areas. 3 times 4 is 12 units, and of course that's units squared. Maybe we want to be a little more particular there. 6 times 8 is 48 units squared. 9 times 12 is 108 units squared. And 12 times 16 is 192 units squared. So those are our values. By themselves, they really are nothing spectacular. But what I'd like to do is now begin to compare these different values, and we'll do that in a second table. So down here in this table, we have the similarity ratio, and what we mean by that is we want to compare the 6 by 8 rectangle with the 3 by 4, or the original rectangle. So the similarity ratio, we can compare that by comparing the 6 to the 3, or the 8 to the 4, that is comparing any sort of corresponding side there. When we talk about the similarity ratio of the 6 by 8 to the original, it's 6 over 3, because we're comparing the 6 to the 3. And that, of course, is equal to 2 over 1. 9 to 12, we have 9 compared to 3. That's 9 divided by 3. And so the similarity ratio reduces down to 3 to 1. And then 12 over 3. And, of course, the similarity ratio reduces down to 4 over 1. Talk about the ratio of the perimeters. To do that, we actually need to compare the perimeters. So we'll start again with the 6 by 8 to the original. So the ratio of the perimeters is 28 over 14. You can see that's equal to 2 over 1. And then 42 over 14. That is actually equal to 3 over 1. And then we have 56 over 14, which is 4 over 1. So for our purposes, the point of this exercise is that these similarity ratios are identical to the ratios of the perimeters. That's important. We'll talk about that a little bit more in a moment. Let's talk about the ratio of the areas. To do that, we need to compare the areas up here. So when we compare the 6 by 8 to the original, we have 48 square units. So that would look like this. Divided by 12 square units. Notice the unit labels will cancel as they always do. We're left with 48 over 12, which you may recognize as 4 over 1. So that's 4 over 1. Then we can compare the 108 to the 12. 108 divided by 12 is actually 9 over 1. We'll put that here, 9 over 1. And then finally we have 192. When we compare the 12 by 16 to the original, 192 divided by 12. And so we'll actually find that that is 16 over 1. So now we see that the ratios of the areas are numbers that are very different than the other ratios. And so that's the question for us today, is how can we compare the similarity ratio to the ratio of the areas. And of course, it's a very simple rule. We find, and we see here in this chart, that the ratio of areas is equal to the square of the similarity ratio. So 2 over 1, if we take 2 over 1 and we square it, that of course is equal to 2 over 1 times 2 over 1, which is equal to 4 over 1. So we see that that's the square. 3 over 1 squared is 9 over 1. 4 over 1 squared is 16 over 1. Very consistent. We can see the rule is very simple. If we know the similarity ratio, we simply square it, and it will give us the ratio of the areas. Now, how do we find perimeters and areas of similar figures? It's very simple. We apply the ratios as we've just learned them. The ratio of any linear feature of similar figures is the same as a similarity ratio. Therefore, since a perimeter is a linear feature, the ratio of the perimeters in two similar objects is always equal to the similarity ratio. When we compare areas of similar figures, again, we just square the similarity ratio. Very simple. Here's the theorem. If the similarity ratio of two similar figures is A over B, then the ratio of their perimeters is A over B, and the ratio of their areas is A squared over B squared. Let's look at an example. Suppose we have a regular pentagon with side 4 centimeters, and we have a second regular pentagon with side 10 centimeters. We're going to ask the question, can we find the area of the larger regular pentagon given the area of the smaller regular pentagon? So we know that the smaller pentagon has an approximate area of 27.5 centimeters squared. In another lesson, we'll talk about how to actually calculate that area, so we have to take my word for it at this time. But if we know that the area of the smaller pentagon is approximately 27.5 centimeters squared, we can very easily find the approximate area of the larger one. How do we do that? First of all, let's find the similarity ratio of the two shapes. You can see that corresponding sides have lengths 4 and 10 respectively, and therefore the similarity ratio is 4 over 10, which is the same as 2 over 5. So that's the similarity ratio between the two objects. In order then to talk about the ratio of the areas, we know we have to square 2 over 5. And so 2 squared over 5 squared becomes 4 over 25. That's the ratio of their areas. Once we know the ratio of their areas, we simply put this into a proportion. 4 over 25 is equal to 27.5, it should say centimeters, which is the area of the small regular pentagon, divided by A, which is the area of the large regular pentagon. Then we solve that proportion for area, and you'll have to take my word for it again. Area is equal to 171.875, which of course is far too precise a number for us, but we'll go with it for now. So once we know the similarity ratio, we can find the ratio of the areas. If we know the area of one of the figures, we can find the area of the second figure by using that ratio. Let's look at one more problem. During the summer, a group of students used a plot of city land and harvested 13 bushels of vegetables that they gave to a food pantry. Their project was so successful that next summer, the city will let them use a larger, similar plot of land. That word similar right there, we have to be mindful of the fact that in the geometry context, it is a very specific meaning. It's not similar as people would typically use that word. In the new plot, each dimension is 2.5 times the corresponding dimension of the original plot. How many bushels can they expect to harvest next year? Let's just get our minds around what that would look like. So if the original plot is some particular dimension, we don't know how big it is. We just know it's some particular size. And that means the new plot would be 1, 2.5 times as long, and 1, 2.5 times as big this way, so you can get a sense of how much bigger this thing is. It's quite a bit larger. The ratio of the dimensions is 2.5 to 1. How do we find that? We simply say that if it's 2.5 times as big, and we don't know how big it was to begin with, then it must be 2.5 over 1. Therefore, the ratio of the areas is 2.5 squared divided by 1 squared, or 6.25 divided by 1. That would look like this as a ratio. So that's the ratio of the new areas. Now we can compare those ratios to the amount of vegetables they harvested, assuming that they'll get the same yield per acre or yield per unit of area. And so we set that into a proportion. As the students can expect to harvest 6.25 times 13. Where'd that number come from? Let's write it out just to be sure. 6.25 to 1, that's the ratio of the areas, is equal to X bushels of vegetables divided by 13. And so we cross multiply, we get 1x equals 13 times 6.25, and that is approximately x is equal to 81, approximately. So that's how much they should expect to yield. Be sure to work through some review problems on your own, and as always, if you have any questions, send me an email.